Hello everyone, welcome back. Chapter 4 of General Biology. This is the nervous system. This chapter, ironically, is very deeply covered when you go into psychology and sociology for the MCAT. It's something that we talk about when we talk about neuroanatomy, when we talk about parts of the brain, the way that the brain sort of fires off its, potentials and signals and neurotransmitters and blah, blah, and this and that. And there's so much stuff going on over there. Now, why are we covering this in biology? Well, first of all, it's in the book. Second of all, it is anatomy and physiology, and it's something that you need to know. And third of all, psychology and sociology usually ends up being one of the last things that people study. So at that point, when you're sort of almost done with your prep, and it's something that I sort of recommend people to save until the end because you sort of just want to fly through it, you don't want to get bogged down learning an entire new system at that time. When you have the time in your schedule in order to actually dedicate serious time to learning something, might as well do it right the first time. What do we know about the nervous system? It's not a rhetorical question. I want an answer.
Central and then peripheral.
Right. So it is organized into sections that serve separate functions. That's the first thing. Second thing is, it is highly specialized. It's highly specialized. Now, you can say that about pretty much anything inside of the body. You can say that the circulatory system is highly specialized, the hepatocytes are highly specialized, but there's something about the nervous system that just makes it a little bit more like elusive, you know what I mean? The action potentials, the membrane concentrations of ions, the sort of way that it sort of fluctuates between states, the way that transmission and communication actually happens throughout the nervous system, it's very complex. There's incredibly delicate science behind how things actually work within the nervous system. And this is something that is best appreciated when you begin studying, right? And from this high specialization, we need to begin talking about the cells of the nervous system. Because unlike something like the circulatory system, where we say we kind of understand that blood flows and oxygen gets dropped off and blood pressure is formed and blah, blah, and this and that, where we look at the top and we look down and we're like, where does all that come from? From here, we're sort of looking from the bottom up. We're saying that we have these cells, we see what they're capable of. How do they arrange themselves in a way that allows them to do their job as best as possible, right? So sort of like a society versus individualistic view of what exactly is going on, right? What are the main cells of the nervous system called?
Yeah.
They're called neurons, or neuroepithelial cells. So the cells in the nervous system, we have neurons. And very specifically, these are cells capable of receiving and transmitting specific electrical impulses. That's it. Forget everything beyond that. At their most basic form, neurons are basically just cells that can bring in and spit back out electrical impulses. And these electrical impulses are converted into things that we may understand, right? Does that make sense? Not that we may understand, that we're gonna look at it and be like, oh my God, it's saying hello, right? It's that our body can understand what's going on, correct? You need to imagine that pretty much everything in the body happens through a method of translation. You are taking DNA, turning into mRNA, turning into proteins for the body to recognize, right? Here you're taking neurotransmitters, they're firing on receptors, that turns into an electrical impulse that a nerve can recognize, correct? Right. And I want you to almost imagine that there is a micro level of physics going on here. That the translation of like chemical potential energy into electrical potential energy, you can almost like imagine that that's going on, right? That this transfer of languages almost, is almost like a transfer of energy, right? There's different fluctuations within the ionic caliber across the membrane, different voltages, different potentials across the membrane that allow for different signals to be fired off at different strengths. The strength of the signal will determine the strength of the response. And this is sort of the way the nervous system works. We're gonna be drawing a lot of diagrams, so if you guys are sat further back, I recommend you come further in and just do it while I'm sort of like getting the lecture ready. Because right now we're sort of just framing our discussion. That's neurons, right? So what do neurons look like? How much space do I have over here?
You have not much space, like right there.
Like right here?
Yeah.
Okay, that's fine. I think that's enough. Let's do it. You guys are done with this? Okay. So that was our first type of cell in the nervous system, and just remember that everything we have going down from here until I say otherwise is just part of the conversation of cells in the nervous system. So this specific diagram is for the neuron. You have a cell body. This is where I draw my most detailed diagram of the entire lecture series. You have a cell body, correct? And you have that. These are different things. So I'm just going to show that by making this a little bit thinner. There. Now you can sort of see that these are completely different things, right? This is known as the cell body, this part right here. It's kind of the command center of the neuron. And the neuron is a cell, so what is that dark thing that I have right there? The nucleus, right? So it's the sort of region where everything really takes place. And this also has a name. The cell body is also known as the soma. It's not a term that we really see anywhere else other than neurobiology, right? And this is where you have your ER, your ribosomes, and your nucleus. Everything that really, quote unquote, happens within the cell happens from here. Now, this is an interesting distinction to make because do you guys remember our conversation about kinesin and dynein? Where dynein dives into the cell, kinesin moves away, right? What is into the cell with regard to this? If I were to move from here into the cell, which way would I go? Left or right? Some people say left. Who thinks left? Who thinks right? It's fine if you're wrong. I just want to know. Because I always thought that we were talking about the dead center of the cell longitudinally. That's always what I thought. I thought that this was where we were moving towards. It's not the case. We're moving towards the body of the cell. The meat and potatoes of the cells where we're moving towards. So when dynein walks across a neuron, it's actually moving that way. This is diving into the cell. That way, right? Almost moving towards the command center, correct? You guys sort of get that? You guys understand the distinction I'm making here? That's important. Because remember, if anyone studied neurobiology here before, would raise of hands who's done like very basic neurobio. Very, very basic. Like action potentials, neurotransmitters, right? Very basic stuff. Remember that the vesicles that need to be transported out of here when we later fire off a response need to be carried out. And if they're carried by something, they're probably not carried by dynein, they're carried by kinesin. Right? So that's a sort of logical pathway that you can take from there, which is why I made this reference. And I made it because I got this question wrong on a practice exam once, and it stuck with me. Yes?
Could you elaborate a little bit more on why the distinction is being made?
Because in the neuron, you're going to have vesicles and proteins and little molecules and sort of packages that need to be carried to different ends of the cell. So you need to know which one is the positive end and which one is the negative end of the cell. Or which one is toward the cell or which one is away, right? So that would be away in the same way that if you started from here, this would be away.
I was assuming that was already like assumed because like it's going down the axon.
Right, so basically, the only distinction I'm trying to make here is that this, if you're moving towards something, this is what you're moving towards.
I see.
And if you're moving away, you're moving in any circumferential direction away from there,
Okay.
right? And of course, I'll always say, as far as I know. This tail of the body is known as the what? The axon. This whole thing right here, and notice where I'm cutting it, and notice where I'm cutting it, is known as the axon. Wax on, wax off. Be very specific when you name things in biology or in medicine in general, because we're about to do something to the axon and it still exists within that thing, but it's not necessarily part of it, because the axon needs to get insulated. We need to wrap the axon in something. So the way we do that is we box it off and we insulate it. And we box it off and we insulate it. And we'll talk about why this insulation takes place in a second. Okay. Do you guys see how this is the insulation? And between the insulation, you can see little pieces of the axon exposed. Yes? So the axon still runs within that sheath, right? The insulation is wrapping around the axon, almost like this. My finger is the axon, we're wrapping like this. It's still there, even though it's covered by something. We are not less than 9 months old. We have object permanence. We know that it's still there, right? We're not playing peekaboo. Okay. The boundary between the cell body and the axon has a specific name. This is known as the... Yes, very good. The axon hillock, or hillock. And this is where your incoming signals are integrated. Has anyone here ever worked as like a secretary before? Anyone? Yeah. So basically you have all this BS coming into the office. Missed calls about like someone didn't come into work today even though they emailed 4 times. And there's a bunch of papers about like some dinner for some person that you don't care about on Sunday. And then all of a sudden, this giant sort of grant money comes through, right? And it's multi-million dollars is gonna save your company. You are the one who needs to filter through all of that and be like, this is what's important, this is what I need to send forward. That's what the axon hillock is doing. It is the secretary that filters all the BS that comes in through the body, right? Because once you send it down here, we're gonna see that there's really no point of return. Once you send it this way, that's a final message, right? Does everyone understand that? The little parts of insulation, and you can imagine why we're insulated, why is this happening? Because as I've alluded to, even though we haven't talked about it yet, all of these signals are made in the way of electricity. There are small voltages of electricity that travel through this cell and out the other end, and that's how we send signals to other parts of the nervous system, right? The insulation makes it so that that electricity doesn't fire off in different directions. Have you guys ever been like blessed enough to see lightning up close? Like really close? I remember one time I was praying in the mosque and I had my eyes like sort of on the floor, but through my peripheral vision, I could see out the window into the parking lot. And I saw lightning strike right in the parking lot. It was crazy. It was like maybe 15 feet away from me. It was wild. But do you guys see that when lightning comes down, it just fires off branches everywhere? Like it's a branch that way, a branch that way, a branch that way, a branch that way. Imagine if all of that was in a straight column coming straight to where it was going. That's what we're doing here. We are basically insulating the pathway to go forward. And the reason we're doing that is because with the signal we're trying to send, we want as much pow as we can possibly get in that signal. Because it is possible that this signal is, please itch your right toe, But it is also possible that this signal is you just got stabbed and we need to clamp down on an artery somewhere, right? So the power of the signal is not only determined by the mechanism by which it was sent, but also how well the signal is able to travel through. And there are many disease processes inside the body that actually attack this insulation, and it makes the signal slower, number one, and number two, it makes the signal weaker, right? You get a weaker signal. Does anyone know one specific disease that attacks these specific insulation points? MS, multiple sclerosis. You can look that up. It's a very, very interesting disease. Very complicated, right? These insulation points are actually cells. And these cells are called what? Huh? These cells are called? Anyone? Schwann cells. Schwann cells that make what? Schwann cells make myelin. Myelin is that insulating material. Does anyone know what it's made of? Like primarily what it kind of looks like in the body? Fat. Fat. In the same way that rubber doesn't conduct electricity, fat doesn't conduct electricity. Which is why we say that lipophilic molecules, like, does anyone here know, I hope you don't, but does anyone here know a person, maybe not personally, or seen a person who huffs gas, who uses gasoline, right? It's a very famous drug in like the late 90s, early 2000s. I don't know if it's been around for longer, probably because it's just gasoline. But what happens is that for my orgo people, if you look at the structure of something like gasoline, octane, 1, 2, 3, 4, 5, 6, 7, 8, it's just a hydrocarbon chain, which makes it very what? Lipophilic, non-polar, right? Not hydrophilic, but lipophilic. And the lipophilic nature of the molecule allows it to dissolve very well inside of the nervous system, which is why it goes straight to your brain and dissolves out, and it just gives you this wicked high, crazy, crazy high. But it also chokes out the nervous cells. And the reason that there's so much fat inside of the nervous system is because of all this insulation, right? Very good. So the Schwann cells are like these actual like cells that make the stuff in between. This stuff in between right here is the myelin. Everything that we're insulating the axon with, correct? That's the myelin. At the top of the cell, looking back now, we have these little spokes known as dendrites. I think they put that there for me. The time has finally come. You guys remember that? Who you guys seen the SpongeBob SquarePants movie? You guys remember that scene at the end where he's like hanging from the rope, where like he's done with his like big song, and he's like, "I'm up here." He's just like hanging from the ceiling. The last thing me and my best friend from high school did before we left for college was watch the SpongeBob SquarePants movie together. Good times. So we talk so much about like the axon, blah, blah, whatever it is. The dendrites are actually the things that what? They receive the signal. These are the specific parts of the nerve that receive, the neuron that receive the signal. And passes it on to the cell body, correct? How are we doing? You guys following along? Good. We talked so much about the axon already. Basically just the thing that sends the signal down the cell, right? It is just one wire. It's basically just a wire. Very low resistance, very efficient, very quick wire, right? We have the nerve terminals, right? These are collectively the, how much space do I have on the board?
You have space.
Okay. The nerve terminals. And this is where the signal gets spat back out. In one of two ways. Either a continuing electric conduction, or more than likely in the way that you're going to study it, it will get spat out. Honestly, not even in a continuing electric conduction. More importantly, in the form of neurotransmitters, which I will refer to as NTs, which doesn't really make sense because that looks like it says nerve terminals, but we'll just write out neurotransmitters. It's good spelling practice for me. This is your dopamine, serotonin, acetylcholine, GABA, glycine, neurotransmitters, all of which we'll talk about. Any questions?
Why do you say spat out, even though it's like gap junctions and stuff like that?
We will talk about how at the end of the nerve, after the nerve terminal, there's basically just a space. It is spitting out the response into that space and just crossing its fingers and hoping it goes.
So this like the club.
That's literally what's happening. It's not like I'm coming here and that's not what happens. It's more like I'm taking a leaf blower and just blowing it into the air and hoping that he goes backwards.
So that's what's happening in the synaptic cleft.
Yeah.
Okay.
The nerve is basically just like, okay, well, here's this big empty room. Someone caught it. Give you guys a second to note all that down. Give you a second to take in how much information there is here. And this is just one cell. One single cell. I don't know how long nerves can get. Really long. Really long. And of course, like nerves form like when you do gross anatomy, when you look at a nerve in and of itself, like they're like, oh, here's the vagus nerve, here's the phrenic nerve, here is the, what's it called? The oculomotor nerve. You're looking at a nerve fiber that is made up of thousands and thousands and thousands of neurons, right? But that specific neuron can actually be like meters long, like a meter long. Like my sciatic nerve, like we talked about before, I think I gave this whole demonstration before, that runs from the outlet of my lumbar spine all the way down to the last part of it reaches my big toe. That's like longer than 3 feet. That's huge. So imagine how inefficient it would be if we didn't have that insulation along the way. Right? Does that make sense?
Yes.
You would lose so much of that signal going forward. It's like a game of telephone, right? Imagine playing a game of telephone, but the next person is like out in the courtyard, and I'm just like, all right, could you tell the guy next door? And he's not even listening, right? Whereas there's literally someone pressed up against me, like right here, and I'm just like, okay, so go outside, walk to the person, make sure there's no one in your way, don't stop for anything, and go tell them that I want a Celsius. They're gonna deliver the message. There's nothing coming between me and the message being sent. And the way that we do that is actually that the message is sent through basically a telephone wire. You would assume that the message just gets sent down the axon and doesn't move out. I like to lie a little bit. I really love lying a little bit so that I can get you ready for the discussion that's coming. The signal actually does what, for the people who know? It jumps. It jumps between the non-insulated points on the axon, right? And these non-insulated points, which I'll denote in red, are very important. And they are called the nodes of Ranvier. Whoever said Ranvier, get the hell out of my classroom. It was you.
I'm a neuromator. Who's right here?
You're right. You know what, guys? Zayd's gonna teach the rest of the class. I'm out. I'm gonna go home. I'm gonna do my self charts. Okay, that's that for this diagram. Does anyone have any questions about what we put on? I know some people came in late. If you want me to re-describe anything that's over here. I feel like this is just a general sort of overview of stuff that you might have seen before. We're just solidifying that, right, before we move forward. Has anyone never seen any of this before? That's good. Okay, awesome. One thing that I want to talk about with the axon hillock, right, is that we're sort of adding on the extra information here. The axon hillock actually works through summation of incoming signals, which we'll talk about later. We'll talk about summation, things like that.
Where you wrote ER, ribosomes, nucleus, like, are you referring to a specific structure?
So all of those are contained within the cell body. The ER, the ribosomes, and the nucleus are contained within this part of the cell. There's none of that over here, because that would just be taking up space where the electric potential is supposed to travel, right? If you're confused about what electric potential we're talking about, we will get there.
For the axon hillock, when you describe it like a secretary, picking and choosing, is it actually like picking and choosing what goes through, or?
So yeah, you have multiple signals that come in, and the axon hillock space is like, it takes all of them and it says, is this enough? Do I want to send this forward? Because that was actually the very, very good that you brought it up, because that was the next thing we were going to talk about. And it sums up incoming signals. Now these signals can be inhibitory or excitatory. And I will say that if the signal is excitatory enough, it gets passed on. If the signal is excitatory enough, it gets passed on. Basically, I really hate getting out of bed. I really, really, really hate getting out of bed. Yeah? Who else hates getting out of bed? Pick the wrong field, by the way. I really hate getting out of bed, but if I don't get out of bed in the future, someone dies. If I don't get out of bed, someone dies. That is enough of an excitatory signal to get me out of bed, right? Okay. Does that make sense? So you need to hit the neuron with something, pow, impactful, right? We need to be able to do that. These specific signals that are excitatory enough, inhibitory enough, blah, 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 this is that, how it changes the microchemistry of the actual like neuron membrane, not really a discussion we're going to get into. This is more like advanced neurobiology. It's probably something that you guys studied in later neuroscience classes and things like that, like the actual potentiation of messaging and what happens at the level of the membrane when the signal hits. Not something you need to know for the MCAT. Interesting, terribly interesting, but not really something we need to focus on. This myelin is produced by oligodendrocytes in the central nervous system and Schwann cells, like I mentioned before, in the peripheral nervous system. So why did I say Schwann cells before? I just felt like choosing one. What is the central nervous system? Is anyone here old enough to remember Schoolhouse Rock? You guys remember Schoolhouse Rock? Have you guys watched the nervous system one? Where it's like the central nervous system is the brain and the spine. The brain is the home and the spine is the line, right? Like you guys should, okay, I want you guys to write this down next to your notes. Schoolhouse Rock, nervous system. You're gonna go home and watch it because there's a cute little song. There's a telegraph line, you got yours and I've got mine. It's called the nervous system. Does this ring a bell for anyone? Come on, man, you guys are so lame. You guys should definitely go watch it when you get home. It's gonna stick with you forever. The central nervous system is, though, a small correction on the childhood cartoon, just a tiny one. The central nervous system is the brain and the spinal cord. The spinal cord, correct? By the way, one of the most well-protected things in the entire body. I told you guys all about the spinal cord, right? Where like in the front of the spinal cord, you have all the viscera and the skin and the organs, the rib cage and whatever it is, and the stomach and whatever. So if you get hit from the front, a lot of your front of the body takes the impact. If you get hit from either of the sides, there are actually little horns that come out of the side of the spinal column, the vertebra, that will fracture and take all of that like force and just disperse it through the body. And if you hit from the back, you have a spinous process that moves backwards and that will fracture, right? So there's multiple points where you have built-in fail-safes into your spinal column that will break before any force reaches your spinal cord. You need a pretty drastic injury to hit the spinal cord. Or a herniated disc. Okay. This is what we have for neurons. And this whole picture, I will now symbolize with one thing, and you need to understand that when I draw this one thing, I'm talking about all of this. Every single thing we wrote here needs to come to mind when I draw this. All of that is this. The body, the dendrites over here, the nerve terminals, the axon, which is naturally insulated. That is what we're going to use for nerves. Because now we don't have the time to draw out all of this stuff. We don't have that liberty, right? Okay. Let's begin talking about the ways that nerves communicate. If anyone would like to take a picture for their own reference, or if you guys need a little bit more time to sort of write down, please feel free.
You could also just slide the next whiteboard down.
Oh, I could. That's so interesting. Should we do it?
Yeah.
I think that's fun. It's like hit it.
Yeah.
I did that one time at Brooklyn College. I came in early, like very early to the lecture hall. I actually locked the door of the lecture hall. I think I did. I either closed it or I locked it or something like that because I didn't want anyone coming in. And I drew out all of glycolysis. Every atom, every enzyme, every step, everything. Every bond, I did it meticulously. And I slid the board over it, right? Because I knew that if I did it live in class, people would have copied it down with me. And I really didn't want that to happen. So I covered it, and we did the whole thing. And when I moved the board, you just saw this full space of just atoms and bonds and movements and enzymes and this and that. And everyone's just like, yeah, no, I'm not even going to try. And that's exactly, I just wanted to kill their spirit. Just a little bit. I just wanted them to feel absolutely horrible about what they've gotten themselves into. Because sometimes you need that.
You should have done it like in a summary, by the way. Just in a very like sentence what it was like.
Sometimes you need that. My glycolysis lecture sucks. If you guys have watched that lecture before, my glycolysis lecture is rough. It's really difficult to get through because I get very into the nitty-gritty. And in terms of carb metabolism, I think we spend about 5 hours on it, on one topic. It's heavy. There's a lot to cover. That being said, when a nerve wants to communicate with another nerve, there's actually a space that exists between them. They're not physically connected to one another. Like I said, it's not a high five, it's a leaf blower, right? And let's say that we're propagating this way, correct? This space between them is actually known as the, yes, the synaptic cleft. Synaptic cleft. And that's just I would say, actually more specifically, the space. Because here you have the nerve terminal, and here you have the dendrites. And if you guys are going to use the proper language, you have the nerve terminal of the presynaptic neuron and the dendrites of the postsynaptic neuron. And all those three things together make up the synapse, right? So the nerve terminal plus the synaptic cleft plus the dendrites equals a synapse. And this is the space where communication occurs between nerves. That the incoming nerve will fire out into the synaptic cleft and attach to the receptors of the dendrites of the next nerve over. This is how they communicate. It's like blowing a kiss, right? Or firing a bullet, depending on which way you swing. It's Texas, so. Multiple neurons in a bundle creates a nerve. In the peripheral nervous system, unless you are a tract, yes, the central nervous system tract, or a cranial nerve, which is a nerve from the central nervous system. Spinothalamic tracts and all the nuclei inside of the brain and things like that, yes, they are bundles, but more specifically, are they wrapped in something, or is it just a localized area of something that's going on? You know what I mean? You talk about the arcuate fasciculus and the MLF and things like that. Are those really nerves, or are they just pathways by which things happen? The MLF is cool. You guys have studied how vision works and conjugate gaze and things like that. So your left eye turns left. Why does your right eye also turn left? There's a very complicated pathway by which that happens. It's regulated by something known as the parapontine reticular formation and the medial longitudinal fasciculus. The PPRF and the MLF. Very interesting stuff. You guys can look it up later if you like. I think it's nice to be exposed to things that you don't know. Unless you actually like your life and you aren't like me. How you doing, buddy? How are you doing, guys? These nerves can be sensory, ouch, motor, move, or mixed, ow and run. Our next mini discussion is something that Zaid made a reference to very intelligently, is the fact that the organization in the peripheral nervous system is different than the central nervous system. That in the peripheral nervous system, do you guys remember, what did I say this was? Cell body, right? The cell bodies of the cell bodies of neurons within the peripheral nervous system collect into things known as ganglia. So cell bodies collect into ganglia. Now, this never really made sense to me because I've only ever seen nerves drawn this way. I didn't understand how you could get to a peripheral nervous system like nerve and all of them would start and end at one place. That's not necessarily the truth. Because you can have nerves that look like this, but you can also have nerves that look like that. That they're coming from central command, processing, and then sending something back out. So this is basically the same exact signal that came from before, processing further down the neuron and then getting spit back out. So some neurons can look like this, right? And some neurons can look like that. So this allows for organization in multiple different ways. So the ganglia can pretty much be located wherever they'd like, depending on how these all line up. Does that make sense? It's a little bit complicated. Not something that's really within the scope, but just so that you can imagine how they line up inside the peripheral nervous system. Yes?
The first one that you drew, that was what? Yeah, the bottom one. Is that considered a unipolar neuron?
I have no idea.
Oh.
I don't know. It's been a long time since I've done neurology, and I also don't care for it. Neurology was very depressing study. Very, very sad study. The neuro ICU is a place I would not mind never visiting again.
Over the gynecologist rotation.
Huh?
Over the gynecology rotation.
I think neurology was the worst rotation I did. 100%. I was very bored and I was very sad. GYN, at least I felt like I was learning a lot. You know what I mean? Basically, like, my entire neurology rotation I was walking up to people and being like, hey, so how are you feeling after your massive stroke? And they're like, not good. And I was like, well, it's about to get a hell of a lot worse. Here's 40 drugs you need to take for the rest of your life. And by the way, could you stop smoking? Meanwhile, they had like a cigarette in their hand. Neurology is not fun, man. But in all seriousness, neurology is a strikingly interesting study. But it is a branch of medicine that I believe requires you to be very good at separating your emotions from the facts. There are certain parts of medicine that require that very heavily, and there are certain parts of medicine that don't. You cannot be an obstetrician that removes your emotions from the field. You won't succeed. It's not possible. You need to form very deep bonds with your patients. You cannot be a family medicine doctor who removes your emotions from the study. You could be a pathologist and not feel any emotions about your thing. You could be a radiologist and not feel many emotions about your... So it really depends on your personality type and also just like what calls out to you. Now that's not to say that you can't be an emotional neurologist, right? I'm not saying that. But I'm saying that you need to be very good at compartmentalizing. Some branches of medicine require a lot more compartmentalization than others. I think cardiology requires a medium amount of that.
I heard a doctor say you have to compartmentalize for geriatric care.
Yes, you do.
It's like the first thing he told me.
Because a lot of people in geriatric care actually don't want to be alive. Guys ready to move on? Once again, we're still talking about nerves. So that was all of our stuff about neurons and how they fire on one another and things like that. And we will talk about the specific physiology and microphysiology and neurobiology of those action potentials and how the electricity actually travels in just a bit. We have a little bit more stuff to do. By the way, you guys need a new fall wardrobe. Uniqlo's killing it. Pretty much everything I'm wearing right now is from Uniqlo. It's great. The sweater, the shirt, the pants, everything.
Which pants are they?
They're like the, I don't know. They're like the cargos.
Okay. I'm wearing them right now.
The gatekeeping is crazy, man.
I'll have to put you on some jeans later. I have to gatekeep them.
Send me a link.
They must be women's jeans.
Nice. Even better. Glial cells are a different type of cell inside the nervous system. Glial cells, also known as neuroglia. I hate how much my G looks like an S. And I tried to fix it so many times, and it just doesn't work. I just can't. Have I shown you? I know there's a lot of new people here. Has everyone here seen how I write the word the? It's my T, my H, and that little loop is the E.
It's like Sanskrit.
So glial cells perform support and myelination. You have astrocytes. You have ependymal cells. Leave a little bit of room, huh?
I pronounce
You say
it
that
wrong.
again. Like,
Ependymal cells?
No, epidemal cells.
Epidemal cells? I don't know. Did you get a 521 on the MCAT? Shut up. You have microglia. You know, get the hell out. And then we have, of course, which we've spoken about before, so we're not going to rewrite the notes over there. We have the oligodendrocytes and the Schwann cells. Reminder, the oligodendrocytes are part of which part of the nervous system? Central, and the Schwann cells are peripheral, right? You guys can just remember, like, do you guys like writing letters? I think letters are very sentimental. I like to write letters. You guys remember PS? Schwann cells, peripheral Schwann cells, right? The astrocytes are for nourishment of neurons, and they form the elusive blood-brain barrier, not the billionaire boys club, the blood-brain barrier. Contrary to popular belief, we are not talking about pop culture. I'm so tired, man. I was on a flight this morning, middle seat. Just got absolutely screwed.
what airline?
My legs hurt so much.
What airline did you take?
American. It was like $100 cheaper than anything else. Unless I wanted to go Spirit and then like lose a kidney.
Frontier is worse.
Yeah, no, I know. The two options like before that were like Frontier and Spirit, and I was like, I don't want to end up on a headline, and then I also want to be able to bring like at least 5 pounds of stuff with me. So American it is. Every single flight I took, I had to check in my carry-on bag because they ran out of space on every single flight. I was like, what? Why do I even bother? Like, if you're not gonna let me carry my carry-on bag, why am I taking up the offer of bringing it? It's just like, imagine I wanted to host a lecture series, and I'm like, we can hold 40 people in the room, and you walk in the room, and it's my apartment. Like, it's my room in my apartment. I was like, all right, 40 people, let's go. Whatever the hell those are cells. Okay, we're also going to call these the whatever the hell those are. So the whatever the hell those are cells, they line the ventricles. Of the brain. And they make cerebrospinal fluid, CSF. CSF is basically the fluid that surrounds, protects, filters, nourishes, communicates with, and does pretty much everything that the blood doesn't do within the nervous system. If you think about your brain and your spine as the spinal cord as a continuous sort of body, right? The whole thing is surrounded by this fluid. And all of it is really produced within these holes, quote unquote, these spaces within the brain called ventricles, which are lined by these cells. And depending on the pressure within the central nervous system and the whole cavity that holds the central nervous system in place, depending on the amount of fluid in there, they absorb or create more of that fluid. This cerebrospinal fluid is actually incredibly important because it allows for us, I love when I say the word important, right? Because my Long Island accent comes out a little bit. I actually don't say the last letter of the word. I don't say important, I say important, right? So it's very important for the diagnosis of certain neurological disease processes. Have you guys heard of meningitis, right? Meningitis, a inflammation and possible infection of the meninges inside of the nervous system that actually can be diagnosed through a lumbar puncture, within which you take cerebrospinal fluid out of the central nervous system cavity and look at it under a microscope or do a cell study on it. Correct? Does anyone know why we're able to do a lumbar puncture, poke into the spinal canal, that sort of space, without damaging the spinal cord?
Isn't there space in the sacral area? Like
Yes. So below a certain level, I believe it's L2, L3, that area, you have the end of the actual spinal cord. So the spinal cord comes as one thing, and then it dips off into this point. And that point actually has a name. This is known as the conus medullaris. And after that, it becomes all of these spaced out, wispy nerve fibers, right? Does anyone know what that's called? This is called the cauda equina, or the cauda equina. It is named after a horse's tail. Cauda, tail, equina, equine, horse, the horse's tail. You can put a needle in there, because when you put a needle in there, the fibers will just move out of the way, and you won't damage any of them. Whereas if you put a needle in here, I guess you're not having kids. Tough.
I could be getting this mixed up, but is that what they do during labor?
Yeah, so you can do a anesthetic. You can inject an anesthetic into the central nervous system in order to numb the entire sensation down there. Question?
No, I was just gonna ask the same thing. Is that where you get the epidural?
Yeah. I totally forgot to message my family that I got back to Dallas. Oops. Let me send this text real quick. Does Dallas have a lot of like stray cats?
Depends on where you go.
Depends where.
We have a ton back on Long Island, so our family group chat is just filled with pictures of stray cats. We've been feeding them since 2009. In 16 years, we've been feeding stray cats.
South Irving has a lot of stray cats.
The stray cats in Long Island are fed well. Like, they're fat.
Have you been to Turkey yet?
No, I haven't. I've been to the Istanbul airport. Great place, by the way. Fantastic place to stop by. Mostly because of the cologne there. But, you know, smelly water enthusiasts unite. But, yeah, no, I haven't actually been to Istanbul itself.
They're everywhere.
I know. In Medina, they were everywhere, too.
That's true.
I used to just, like, pick them up off the street and walk with them.
But they treat them worse in Medina.
Really?
Yeah.
Oh. I saw this one with, like, just crust on its eyes, like, just woke up. It's so cute. I miss my cat, Sage. Okay. Then we have microglia. These are your phagocytic cells. Your garbage disposals, right? They ingest waste and pathogens. And microglia are really just specialized macrophages. It's a phage, macrophage, right? Phage, macrophage, right? But I also use that for other stuff, so like neutrophil, basophil, neutrophil, basophil, eosinophil. You guys getting used to my little shorthand? Do you guys remember what these mean? So this means after, and this means, this means before and this means after. I haven't spelled them out myself. So like, why does this mean after? means post. After, post. And this means French avant, before. And this is actually, it's not post, but you can think of it that way. This is actually après. Avant, après. Before and after. And my favorite one of all time is, of course, therefore. Yes?
So are microglia just like cells that are mostly lysosomes? Or
No, like, you know how macrophages literally like ingest things and like break them down and blah, blah, whatever, either through peroxisomes or lysosomes or enzymes or whatever it is, basically just specialized versions of those. All good? What time is it?
5:38.
Oh, not bad. Cool. Let's get into the meat and potatoes of this lecture. Now we have the necessary information we need in order to understand signal transmission. This is where we talk about action potentials. Action potentials are all or nothing messages. Right? That relay electrical impulses. Down the axon, correct? There is a law of biology, of cellular biology, that applies to every single cell within the body. The membrane of a cell has a voltage. There is a potential. There is an electrical difference of charges across the two sides of the membrane. This is tightly regulated, and one of the most important characteristics of a cell in terms of its cellular physiology. The entire physiology of a cell can be changed by modulation of this voltage that exists between its membrane, between the outside and the inside. In the study of action potentials, we actually begin to take a look into the way that this voltage can be modulated and changed in order to send signals. Did anyone not understand that? Very good. So every neuron has a resting membrane potential. And this is a net electrical potential difference basically a charge separation, right? That exists across a cell's membrane. And this is, in the neuron, approximately 70 millivolts. Sorry, negative 70 millivolts, correct? Yeah, negative 70 millivolts. Meaning that the inside is negative relative to the outside. Everyone understand that? Perhaps there are more negative charges outside. Sorry, perhaps there are more negative charges inside, or perhaps there are more positive charges outside. And this is what's causing the difference in the potential. Now, if you think about this in terms of straight concentration of ions, that means that there's going to be a fight for the potential to equal out. And there has to be a fail-safe mechanism within the body to resist that urge for neutrality, right? You know anyone who's an instigator? We all know someone. Maybe they're sitting in this room with us. Maybe they're right in front of me. Maybe they're the reason I have a continuing crippling caffeine addiction.
I think you did that one too, so.
Watch your mouth. See me after class.
He's instigating.
I'm instigating. If you want to instigate, if you want to keep things out of balance, you have to put in a lot of effort. The natural order of life, humanity, society, this, that, the other thing, is very neutral. If you want to completely F up everything around you, you got to put in a lot of effort to do so. Right? Like if you wanted to completely throw me off my track and make sure that I get nothing in this lecture correct, you would have to undo 4 years of teaching. It's not going to happen. No one's going to throw me off my game, except for myself. Right? So, given that the body really, really wants to maintain a neutral sort of balance between the outside and the inside of the membrane, how is it that we actually maintain this negative concentration? What time is Maghrib again?
7 something.
Oh my god, back in New York it was like 6:25. What time is it today? 7:06? Okay. We'll stop at like 6:15. And I'll just put these two together. This negative potential is maintained by a delicate balance between sodium and potassium. I want you to know that the concentration of potassium inside is greater than the concentration of potassium outside. And the concentration of sodium inside is less than the concentration of sodium outside. Neuro people, please double check me on that. And this inherently means that the sodium wants to move where?
Oh, it moves out.
Moves out in the way of the arrow. The potassium wants to move, did I say sodium? Is that what you got mixed up? I'm so sorry. The potassium wants to move out, because it's higher inside, lower outside, it wants to move out. The sodium wants to move in, higher outside, lower inside, wants to move in. This is strict diffusion. We're not talking about any complicated process here, right? We're talking about strict diffusion. The concentrations are higher in one part than the other. It wants to move from the high to the low. Done. That is a desire of the actual chemistry within the body. This is how chemistry works, right? There's a whole calculation that's done, neurobio people, you've done it, where you looked at the actual potential differences, looked at how much of them leak at any given moment, look at the equilibrium of exchange between the two ions, see how the negative potential for potassium and the positive potential for sodium actually equals out to -70. It's a very complicated process. It's not something you need to know for the MCAT, but if you'd like to look at it, there's actually a mathematical calculation by which that's calculated. The -70 isn't just some random number, right? So the negative potential difference isn't really a negative charge. It's more so a net movement of ions in a certain direction. Now, the majority of the positive ions that make up these voltages exist outside of the neuron. And since you have a higher population of those positive ions outside of the neuron, it's making the inside of the neuron relatively negative. Relatively negative. There is a relative negative imbalance, right? How is this negative potential maintained? The maintenance is done by, and I want you to forever write it this way. You will never write this. Sodium potassium pump. Never again. You will call it by its proper name, sodium potassium ATPase. That is the proper name of that protein slash enzyme slash whatever it is, right? That pump. This is the proper name, and by writing it this way over and over and over again, you will drill into your mind that the energy investment from the ATP maintains that gradient. That there needs to be energy put in to maintain something that is outside of what is desired. Yes, because we know from general chemistry that charges are not a desirable form of existing. Should we take a break? Because we're going to move on to the actual action potential table now. Let's take a break, and then we'll merge the two videos. 5-minute break, 10-minute break for the Muslims to go pray, and everyone to catch a coffee or a snack or whatever it is. And we'll be back. Thank you guys so much for watching. We'll be right back.